All right. So I started to allude to this at the end of class last time, that we've kind of reached a point in the class where we're just set them together. It's fine. So as long as your name's on the first page. Where it's fun time, right? We're just doing fun stuff? No. This is kind of like the miscellaneous sections. So there's not going to be like a natural flow to what we're doing. You know, in the past we did like, okay, these are the trig functions. Now here's like trig equations and trig identities, and everything just kind of like was connected. Now we're just kind of going to grab topics from all over the book. And this is kind of what we would have done in the beginning. And I told you on the beginning, I don't like to be going all over the place to start the class. So now we're going to do it. But I looked back real quick in 10.4 on page 752. Just said it. It's all right. Yep. On page 752 at the very beginning, in the top of the section, they have these things called objectives. The objectives of the section. And they list out, I believe, 7 objectives in 10.4. 6 objectives. 7. They have 7 objectives. You need to know how to do the first 6 objectives. So like the first one, graph a vector. Second, find a position vector. Third, add and subtract vectors. Fourth, find a scalar multiple and magnitude of a vector. Fifth, find a unit vector. Sixth, find a vector from its direction and magnitude. If you can do those 6 things, then you'll be prepared for what I might ask you on the final. All right? Polar coordinates, that section we talked about last time, page 720. There are the first 3 objectives are what you should know. All right? Now we're going to move on to chapter 12, section 5, which is just kind of random and out of nowhere, but that's what we're going to do. All right, everyone got this? All right. That's what we're talking about today. Something called partial fraction decomposition. Sounds pretty bad, doesn't it? Partial fraction decomposition. And, well, let's see what it's about, all right? So let's start with an example. And keep in mind, we are, like I said, we are going to be going from topic to topic, and it's going to seem disconnected. This is going to seem like we're back in college algebra, right? There's going to be no trig here at all, right? No sine, cosine, none of that. It's all gone. No vectors, no polar coordinates, all right? So here's what I'd like for us to do. I'd like for us to add these things together. Here we go. I want you to add 4 over x plus 2, add that to 1 over 2x minus 1. Common denominator, that's right. Okay, so I heard what I wanted to hear. If you're going to add 2 fractions, you have to have a common denominator, don't you? All right, so the common denominator is going to be both x plus 2 and 2x minus 1. I'm going to need both of those factors in the new expression. So what I'm technically doing here is I'm multiplying this fraction on the left, top and bottom, by, 2x minus 1. That's what it's missing, right? And I'm multiplying this by 2x minus 1 on top and bottom. And then on this fraction, I'm multiplying the top and bottom by x plus 2. Agreed? I should probably throw some parentheses around these, because when I multiply those two, I would need the parentheses side by side in order for it to be written correctly. All right, let's do this. Let's multiply these two together. So go straight across. The 4 would distribute through that parentheses, and we would get 8x minus 4 over the common denominator, which I'm not going to multiply out. Well, yeah, not yet. I'll multiply it out in a second. Plus, now I'm going to, oh, it's a 1, so that's going to be easy. 1 times that's just x plus 2 over the same common denominator, 2x minus 1 times x plus 2. And now that they have the same denominators, I can add them, right? So I just add the numerators up. I do 8x minus 4 plus x plus 2. So what's that? 9x minus 2 over the common denominator. But I'm going to go ahead and multiply it out now. Okay? So let's multiply this out and see what we would get. 2x times x is 2x squared. And then 2x times 2 is 4x. Then I'd have to take away an x, so I think I'm going to get 3x there in the middle. And then my final term there is minus 2. This look familiar to you? Okay. All right with it? This is not what we're doing. What we are doing is we're going to start here and get to the original problem. We got to go backwards. That's what partial fraction decomposition is, all right? It's much harder than what we just did. And here's what makes it hard. Let me write the original problem. The original expression was this. Okay, that was the original expression. How do we get from here back up here? So if we were just to kind of retrace our steps, the first thing that we did was we did this, right? I mean, like, we would have to go back to this. So this 9x, right? That came from taking 8x and adding x, right? But that's not the only way I could have got 9x. I could have done 6x and 3x, right? 5x and 4x. How do I know it's 8x and x? This 2, minus 2, came from minus 4 and plus 2. There's an infinite number of ways that you can get negative 2, right? You can do negative 6 plus 4. So how do you go from here to here? It's actually very difficult to do. Do you see the problem? So what do? Well, we have a whole process called partial fraction decomposition. All right? You ready? Look, does it look fun? Yeah, you want to go back to trig functions? All right, so let's start out with the expression 9x squared over 2x squared plus 3x minus 2. Now look, if you read the book, they're going to sit there and spend like a bunch of time trying to explain like this process, which is fine, but I'm more inclined to show you some examples, and after we do some examples, we'll start to establish a process. All right? Because if I just give you the process right now, I have it on my notes, I could show you, and you'll look at it and just go, what the, you know? Okay? So we're going to start here. Our goal is to end here. By the way, this is a unique representation. There's not like multiple ways to represent that, like to turn it into a broken up fraction like that. There's only one way to represent it. So we aren't going to get different answers. We're all going to get the same answer. All right? Okay, so here's the procedure. And I'll write it down later. I'm just verbally going to say it for now. First thing we're going to do is we're going to look at this, and we're going to check to see what the power of the numerator and denominator are. All right? So let's just do a quick check. The numerator we call it, the power is the degree. Okay, so the degree of the numerator is 1, because the highest power of x is 1. The degree of the denominator is 2, because x squared, right? So the degree up here is smaller than here, yes? In that case, we just proceed to the next step, all right? I'll show you an example where we have to do something else. But in the event that this is smaller than this, we proceed, all right? Now, I'm going to factor the denominator if I can. So my question to myself is, does this factor? Because, right, didn't these come from the factored? So let's factor the denominator. And does it factor? Yes, it does. Should I try and explain right now why you would need to do this like later or no?
Yes.
I'll just make it very simple. In Calculus 2, we have a problem that we're trying to solve, and we're looking at this right here, and it's very difficult to do what we need to do to this. Like when we look at it like that, we're like, ooh, can't do it. So what we do is we rewrite it like this. And once we rewrite it like this, it becomes like a 1 + 1 is 2 problem. It becomes very simple. But the process, you have to be able to get from here to here to be able to do the good stuff. So it's very valuable in Cal 2 to make a hard problem easy. Make sense? In this class, all we want to do is make sure we know how to get it from there to there. In Cal 2, you just kind of do it. Like, depends on your teacher. I usually do show my students, remind them how to do it, but some instructors will just be like, this line becomes that line, and they don't show you how that happens. They just say, oh, it's partial fractions. All right? Okay, so we factored the bottom. Now comes the fun part. I'm going to go ahead and rewrite it again. Do you all know what a linear expression is? Linear expression is something that looks like a line. The highest power of x is 1. That's linear, right? Quadratic x squared, that would be, yes? Okay. Do you agree that right now, what we have in the denominator are two linear factors? This is a factor, and this is a factor. We call them factors because there's multiplication. So this is a linear factor, yes? This is a linear factor. And they are different from one another, right? It's not the same linear factor. Like this isn't like x + 2 times x + 2. So what we call these are distinct linear factors. I'm not just telling you that for fun. It's part of what we need to understand here. What we have here are two distinct linear factors. That's a good blue marker right there. Two distinct linear factors. Distinct meaning different. Linear because they're linear. Factors because they're multiplied together. Two of them because there's two of them. Right? We could have 3 distinct linear factors. We could have 4 distinct linear factors. In this case, we have 2. So when we have 2 distinct linear factors, the next step for us is to say, all right, well, this should break down to become 2 fractions. Now, we know it's going to because we knew where it came from. But what's telling us that here is the fact that we have 2 distinct linear factors. That tells us it's going to add up to be 2 different things. And we also know, because they're 2 distinct linear factors, that one of these denominators has to be one of the factors, and the other denominator has to be the other factor. All right? The only thing left for us to resolve is what would belong up here and here. And if these are linear factors, then the numerators have to be the next thing down from linear. Okay, so like if you had quadratic, that's squared. If you step it down, it's linear, right? If you step linear down, it's constant. Yes? So what I know is that I have a linear factor here, and the numerator should be 1 degree less. We know it's a 4, right? But I don't know that yet. So I'm going to put, well, it could be any number. I'm going to call it A, all right? And then here, this is B. I don't know what it is. It's going to wind up being a, oh, sorry, that's not a 4. This A is actually going to turn out to be 1, isn't it? And these have to match up. X + 2, B is going to wind up being a 4. So we're at the point right now where we have to now determine that A is going to be equal to 1 and B is 4, all right? But do you have any questions on where this actual setup came from looking at this? We're good? Okay. The next thing we're going to do is we're going to clear all the fractions out. So we have an equation here, don't we? We can multiply both sides of the equation by anything we want. So I'm going to multiply it by the LCD, by the least common denominator. All right? This is the least common denominator. So I'm going to multiply that here, multiply it here, and here. And that should eliminate all fractions. Here we go. I'll do it in a different color. So when I multiply this one by 2x minus 1 times x plus 2. Multiply on this side. This one's going to get hit with the 2x minus 1 times x plus 2. And then this one's going to get hit with the 2x minus 1 times x plus 2. What is left, what remains on the left-hand side when I do this? Just the 9x minus 2, right? This basically just, they're all gone. I get 9x minus 2. Must equal. Now, what happens when I multiplied this factor, or this term by this? What cancels? The 2x minus 1's cancel, don't they? And I'm left with a times x plus 2. Understand? And then when I multiply, or did this over here, LCD here, the x plus 2's canceled, and I'm left with the b, and then times 2x minus 1. That all right? Our goal is to find a and b right now, isn't it? Well, the problem with that is that we have a single equation, and we have three things we don't know. Like, we don't know what x is, we don't know what a is, we don't know what b is, right? So now what we're going to do is be very, very clever. Extremely clever. I'm interested in finding a and b, right? X, I kind of have control over. I can let x be a variable, but I can kind of make it be whatever I want it to be. You get to kind of play God here a little bit, all right? And control x however you want. So let's see. If I would like to find a, I would really like it if this whole thing wasn't even here, right? If this whole thing was not here, like b was gone, then I would be closer to solving for a. So let me choose an x right now that would kill off b. So I'm trying to find a. So I'm going to kill b. So I'm going to have to let x be something to make that happen. So what would make b, this whole term, go away? Well, can you make this factor right here 0? How?
By making x equal to 1/2.
X is a half. Do you agree if I let x be 1/2, this will be 2 times a half, which is 1. 1 minus 1 is 0. So a very clever choice of x being 1/2 should eliminate the b term completely. So this is where you get to play God. Let x be 1/2. You don't have to use that voice. Okay? So I'm going to let x be a half. And I'm going to rewrite this equation. I'm going to replace every single x I see with a half. Okay? So it becomes 9 times a half minus 2 equals a times a half plus 2 plus b times 2 times a half minus 1. Now we already know that this is 0, right? And we already know that that's going to completely eliminate that. That's why we chose x to be a half. Everything else we have to figure out. So this is going to be 9/2 minus 2 equals a times 5/2. I went ahead and I had to get a common denominator here. A half plus 2 is the same as a half plus 4 over 2, which is 5 over 2. So I'm trusting you can add fractions. And over here, what's 9 minus 2? What's that? That's also 5 over 2. And then now, we'll just divide both sides by 5 over 2, right? Because this is multiplication. Divide both sides by 5/2. 5/2 under here becomes a 1. 5/2 under here becomes a 1. So you get a is 1. Yay. We know what a is. Now you get to go get b. How do you get b? Play God again. Come back to this right here. And this time, kill this. So how could you kill this? Let x be -2. So we're going to rewrite the whole equation, replacing x with -2, and see what happens. Understand? So we get 9 times -2 minus 2 equals a, then -2 plus 2, then plus b, and then 2 times -2 minus 1. Just be careful. I mean, you have to replace everything with -2 there. That should kill this a term completely off. What does my left-hand side become? -20. Equals, and then this together right here I believe is -5. So you've got -5b. And if we divide both sides by -5, you get b is 4. There you go. So now you have to come back here and you have to give the answer, okay? So this is equal to, remember we said it was 2x minus 1 on the bottom, then we said it was x plus 2 on the bottom, and then we said a was on top of that one and b was on top of this one. So make sure you get those right. You can't mix them up. So a was, I forgot, 1? Okay, and b was 4. There. We have done the partial fraction decomposition of that rational expression. You like it, don't you? Any questions?
Probably gonna have to reteach us how to square.
For what?
Factoring and stuff.
Oh, the factoring? Yeah, well, yeah, we're not going to do factoring here, so factoring just never goes away, right? It's constant pain in your side or other places. So what did y'all think of that? Well, y'all don't seem too enthused. It's going to get harder, is that what you said? A little bit, yeah, it will. Okay, so let's try this. Instructions here are to do partial fraction decomposition on this. Find the partial fraction decomposition of that rational expression. So, bless you, what was the first thing that I said you should look at? The degree. The degree of the numerator is 1. The degree of the denominator is 3. So in that case, we move on, all right? Don't even worry about doing anything. Just go to the next step, which would be to factor out the bottom. All right, so maybe you just need to do this real quick on the side. I'm taking x cubed minus 2x squared plus x, and I'm trying to factor that. I see a GCF. Y'all see a GCF? I can pull an x out. And does that quadratic factor? It does. It factors to be x minus 1 times x minus 1 again, doesn't it? It's the same factor, right? It appears twice. Okay, so let's rewrite this. This is x plus 2 over x times x minus 1 squared. That x minus 1 is actually times itself, so that's squared. So what we have here is a linear factor. And then this one is a repeated linear factor. So just a quick little quiz, not literally a quiz, but if this had not been squared, we would have what there? This would be, yes, but I'm saying what would we call these? These would be two distinct linear factors, right? This is a linear factor, that's a linear factor. They are different from one another, and we would have two distinct ones. And so I would be saying that this turns into an x down here, and then an x minus 1 here, and I come up with an a and a b, and that I would do exactly like what I did in the previous problem, right? If that wasn't squared. It is squared. So we don't do that. What we do, don't worry, when I do enough of these, you'll start to catch on, all right, to what you do at this step. Well, this one is a linear factor, right? And it's different from this one. So I will put an x here and some number on top. I don't know what that number is. Then I've got this weird repeated linear factor. How many times is it repeated, by the way? Twice, right? So here's what you do. You put plus, and then you're going to put the linear factor down here with a b. And that looks very much like what I just said you would have had this not been squared, right? But then you're going to add one more term to this. And it's going to be the repeated linear factor squared. And then on top of that, a third number that we don't know, c. So let's see if we can't wrap our heads around what just happened. This right here was a linear factor, so I did a over x. Good? That okay? Then what I did is this was repeated twice. So I start out by writing the factor as a linear factor with a number on top that I don't know. Then what I do is I rewrite the factor again, bringing the power up once to squared with another number. But I stopped there because it was squared. Had this been third power, I would have had this, this, another plus, a d, and then x minus 1 cubed. Make sense?
Who figures this out?
Somebody has suffered already for you. All right, understand that? I'm about to give you the formula in a second. You'll see kind of where it's coming from. So you've got this to this power, right? So you're going to write it down with a number, and you keep doing that, bringing the power up until you reach that highest power 2, or whatever it is, 2, 3, 7. What if that was to the 7th? b over x minus 1, c over x minus 1 squared, d over x minus 1 cubed, e over x minus 1 to the 4th, right? All the way to the 7th power, and then I'd be done. Fun? All right, we are good with this. We have exhausted all of the factors, and now we're ready to move on to the next step, which is to clear the fractions. So multiply through by the LCD. So we're going to multiply this times this, 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 and this. What is going to appear on the left-hand side? Just the numerator, right? This is going to happen every single time you do this. When you clear fractions, this numerator is always going to be your left side. So I have x plus 2 equals, now I will help out here. What I did is I'm multiplying this by x times x minus 1 squared. multiplying this times x minus 1 squared, this times x minus 1 squared, this times x minus 1 squared. That's what I'm doing, right? Everything got hit with that? So when you hit this one with this, what goes away? Just the x. And you still have the a, and you still have x minus 1 squared, don't you? Understand? What about this one? Does the x cancel this time? No. The x minus 1? One of them does. So you'll still have a b here. You'll still have the x. And you'll still have one of those x minus 1 factors. Plus c. Now here, the x minus 1 squared and x minus 1 squared do cancel, and all you're left with is the x and the c. So cx. Y'all okay with that? Now you do what? You need to find a, b, and c now, don't you? Right? Because what we're saying is the original expression should turn into some number over x, some number over x minus 1, and some number over x minus 1 squared. That's what it should break down to be. That's the decomposition. So we need to find a, b, and c. So how do we do that?
You have to kill 2 of them.
You have to kill stuff, right?
B and C? You're looking for A, or just 1?
Yeah, but we're going to have to go one at a time. We have to go after them one at a time. So this is where I could say, all right, how could I determine what A was? What would I need to do to get A? That would mean kill these off, right? Can you kill these off?
Yeah.
Simultaneously?
Yeah.
By what?
0.
If x is 0. Do you agree? If x is 0, that's gone. If x is 0, that's gone? Okay, so let's do that. Let x be 0. There was this game that I played when I was a kid on a PC. This was a long time ago, so this is like to move around the map. I don't even remember what the game was called, but to move around the map, I had to use the cursor keys, to move. But I remember there was this cheat. There was a cheat on the game that would give you all like the weapons and all the health, and you just had to type in a string of words, and it was "make it so." That was the golden password. So if you type in "make it so," you had everything. So I always think about that when I'm letting x be 0. I'm like, make it so. We're in total control, right? We get to let x be whatever we want it to be. See what happens. What do you get? 2 equals a. Okay, 0 minus 1 is still negative 1. And then we're going to square it, right? So it is going to become positive. Then everything else is dead, isn't it? And that means a is 2. Right? Good. Happy to see that. A is 2. We are on our way. Feeling all confident about our new deity powers, right? And then we go try and get B, and we realize we are humans still. Why is B going to be a problem? Yeah, look, if you're going to try and get B, that means you're going to have to kill C, right? And the only way to kill C is to let x be 0. But if you let x be 0, you're going to kill B. So you can't get B, right? Can we get C?
Yeah.
We could get C by killing both of these. How can I kill both of these without killing C? If x is 1, right? So let's try that. Does everyone understand that B is a problem? B, it's looking like, is difficult to get, but we can get C. So we're going to let x be 1. Make it so. If x is 1, the left side of the equation is 3. The right side of the equation If that's 1, it's gone. If that's 1, it's gone. And hey, c times 1 is c. c is 3. Dang. We're just cranking away, aren't we? Except for b. So we have a problem at this point. Like, how do we get b? Right?
Could we just substitute A and C?
Okay, so we know a is 2, so we could put a 2 here, right? And we know c is 3, so we could put a 3 here. And that would leave us without the a and the c there. There would be numbers. And then we would have x's mixed with b's, wouldn't we? Let's just try that. Let's just write that down and see what happens. So if I leave x plus 2, I'm going to replace a with 2. So 2 times x minus 1 squared. And then plus b, I don't know, x times x minus 1. And then c we found to be 3, right? So this should just be 3x. Do y'all agree with that? So why don't you try and get b right now by playing God again. Maybe God's too strong of a word. I don't know. Not trying to offend anyone here. I'm kidding around. Can you get b by choosing x? And see, you don't have to worry about a and c anymore. A is 2 and c is 3. So just pick a clever x right now. Just any clever x that won't kill things off, but will be easy to compute. Okay, 1 will kill these off though. 2, how about 2? Let's try 2. Let x be 2. Now, why is 2 a clever choice? 2 minus 1. 2 minus 1 is 1, isn't it? And 1 squared is 1. So that'll be an easy computation. I could have picked x as 5, but then I do 5 minus 1 is 4. 4 squared is 16. So I start getting bigger numbers. But let's just see what happens when x is 2. The left side should be what? 4 equals, and then plug your 2 in here. I already said 2 minus 1 is 1 and square it. So what would we get? What would this piece be when we plug 2 in there? 2. Okay. Plus, now here I have to plug the 2 in, and I have a b there. So doesn't this become 2b times 1? So just 2b. And then down here, what does this become? 6. And I believe from there you can move things to the other side and solve for b, right? I believe you're going to get b is negative 2. Can somebody confirm that? Yes? Okay. And so we have our answer. We have our partial fraction decomposition, don't we? So the original expression breaks down to be, we need a final answer here. It's a over x, so 2 over x, b over this, so negative 2 over that, and then c, which is 3 over this. So this is our answer. That's the partial fraction decomposition of that rational expression.
So if you factored out an x squared on a different problem, do it differently, or?
If you're saying, like, if this GCF would have been x squared, that's your question? Had this been x squared, then I would have had a over x plus b over x squared. No, nope. If they're not both quadratic. I mean, if they're both quadratic, you have to do the same thing. Yes?
So I followed the math, but I have how can you do what we've done? What's the reasoning behind it? Because you basically mapped your x value to 3 different values.
Yes.
Is that fair to do it?
Well, you have an equation that has to hold true, right?
Right.
And you have 4 different variables in there, a, b, c, and x,
Okay.
right? if you're going to try and figure out what a is, you're free to do whatever you want with the other variables. I mean, it's like, think about it this way. Let's just say I wrote this down. X plus y equals 4. Let's just say I wrote that down on the board. You have two variables, right? There are an infinite number of answers to this that you could come up with. Like x is 2, y is 2, right? You could go 3 and 1. You could go 4 and 0. So one way you could do this is you could just pick a value of y, right? Like let's just pick a value of y. How about we say 3? And now solve for x and you get x is 1, right? All we're doing is we're taking an equation that contains 4 things we don't know, being very clever in picking an x that's going to eliminate 2 of the things that we don't know and leave us with 1 thing. So it's just like over here, substituting in a y to get an x. We're substituting an x in to get an a or maybe a b or a c. So we have to think about what we're going after to determine what x we're going to pick. Does that make sense? You're satisfied with that answer?
Sort of, yeah. I'm putting a pin in it until I get to higher math.
No, but I mean, if it's, what's troubling you about it? You feel like we're not allowed to control the x that way, or?
We can, but then we're controlling it in an equation, but we're making this part of the equation equal this, and this part of it equal this. And because we're kludging it, it seems like it's breaking the rules.
Yeah, no, we're not.
I see what you're saying.
Yeah, I mean, we're not breaking rule. We're just being clever in how we pick the x. Like, right here with this equation. Let's just say I picked right off from the very beginning, okay? Forget all the other stuff. Let's just say x is 2, right? Let x be a random number, and I'm going to pick 2.
Right.
Not even worry about killing anything off. Sure. Then if I let x be 2, this equation is going to become 4 equals, then 2 in here, it's going to be 1. You're going to get a plus 2 in here, and you get 2b, and then plus you're going to get 2c. That's what you would get if you let x be 2.
Okay.
So if x is 2, this equation must then become this equation.
Right.
All right?
Right.
This doesn't help me solve for a, b, or c because now I still have one equation and I have 3 things I don't know.
Right.
So what we've done is we've chosen the x in a way that we know that this new equation we're going to get is only going to have one of these letters in it,
Okay.
as opposed to all 3. And there's nothing wrong with that because this is an equation. I plug in a number. As long as I don't have division by 0 or square root of a negative number, it's legit. I don't know if,
Yeah. So if you put it all on planes, it would look at an intersection of all these possibilities, and that's how you're narrowing it down to where those different.
Did you say planes?
Planes.
Like sheets of paper planes? Okay, yes, that's exactly what we're doing.
Okay.
So
you're seeing that.
I think I'm going to satisfy your curiosity right now because I was just about to show you
Where it goes.
the other way to solve this same problem, okay? And I'm not just making that up because you asked. This is standard practice that I do every time. So here's the problem. We kind of got lucky. We were able to get A and C, right? And then from that, we were able to get B. But there are problems that I could give you where you can't get any of them. Like if you try and get A, you'd have to kill everything off to get the A. Like, you know how we couldn't get B because you would have to kill off B to get B? Like you couldn't kill these two? There are problems I can give you where none of them can be killed. Like you can't do anything without killing everything. So there has to be a better way. So this method that I've shown you where we're like choosing the numbers and kind of playing God for a while, I refer to that as the shortcut. That's the shortcut method because it's quick and easy when it works. Like the first example I did, 2, we just let x be this, let x be that, we were done, right? That's quick and easy. But what happens when it becomes more complicated? We need a more powerful method, and that's what I'm going to show you right now. This is the long method. But I think it's going to answer your question. Okay, so please, if you don't mind, let's back ourselves up to this equation before we were letting x be anything, right? This was after we cleared the denominators. Yes, cleared the fractions? I really hope that you'll appreciate this more. We'll see. I don't think you will. None of my students ever like this method, but here's the thing about the method I'm about to show you. It always works. Okay? If there's a solution, if there's an A, B, and C that work for this, this will get it. The shortcut doesn't always work, but it's short and it's fast. All right? All right, so here's what we're going to do. We're not even going to think about killing things off. We're just going to do some algebra here. All right? So check this out. This is, I love this. All right. So you just tell me what I'm doing, and then we'll proceed. Okay, so just tell me what I did there on that line. I expanded x minus 1 squared, right? I did that. X minus 1 times x minus 1 is that. Here, bx, I multiplied it through, right? bx times x, bx times negative 1. I got these two terms. And then cx is by itself, yeah? What I'm doing right now is I'm expanding it all out. I'm going to multiply this whole thing out. It's going to look disgusting. Okay. So now I distributed the a through that parentheses here. So ax squared plus 2ax plus a. See those three terms? These three. And then I have the bx squared minus bx plus cx. All right. Next step. Keep this equation coming. X plus 2 is on the left side. In fact, I'm going to give myself a little bit more room on the left side. X plus 2 is here equals. Now what I'd like to do is kind of collect like terms together. So watch what I do on the right side. ax squared plus bx squared. So I'm getting all my x squareds together. Minus 2ax minus bx plus cx. Then plus a. So you see how I've kind of grouped everything together like terms? These guys had x squared in them. These guys had x's in them. And this guy right here was the only thing that didn't have any x's, right? Okay, check this out. All right, can you tell me what I did here? I factored a GCF. So look at this right here. You see these? I focused all my attention right here on just these two. And I said, all right, look at these two. They both have an x squared, right? So normally we'd pull the x squared out to the front, wouldn't we? I didn't on purpose. I just pulled it to the back. But it's the same thing, isn't it? So that x squared would distribute back through here and give you that. Then I put a plus sign. And then what I did is I looked at these three terms, and they all had x's, right? So I pulled an x out of those, and I slapped it to the back, and I put the three things that were left in parentheses here. So that x would go here, here, and here, and I get back those three terms. Yes?
Yes.
And then I have a like this.
Yes.
And you're probably wondering why I'm doing this. This is an equation, right? Left-hand side, right-hand side have to balance out, right? They have to be the same in order for this to be a true equation. So now come back to the left-hand side and take a look at this left-hand side. And squint your eyes and please see the following. That's really 0x squared plus 1x plus 2. Right? Isn't it? If the left-hand side and the right-hand side have to be equal to one another, do y'all see that? If the left and right-hand sides have to be equal to each other, then the coefficient sitting in front of x squared here must be the same as the coefficient sitting in front of x squared there, which is a plus b. right? The coefficient sitting in front of x, the number sitting in front of x, 1, must be equivalent to the coefficient sitting in front of x here, which is all that stuff. And finally, the number that has no x on it has to match anything over here that doesn't have x on it, which is this. Do y'all see that? And what you now have are 3 equations and 3 unknown variables. I'm going to write them down. The first equation comes from the first expression here. 0 must equal this, right? So I'm going to write that down. A plus B must equal 0. Now, why do you think I left a gap in there? Because I've got C's also. What is the second equation saying? Or the second piece saying? Negative 2A minus B plus C must equal 1. Negative 2A minus B plus C must equal 1. And then the last equation, what does it say? A equals 2. You have a system of equations. 3 equations, 3 unknowns. Now you were asking me a second ago, intersection of planes, right? That's exactly what a system of 3 equations and 3 unknowns is. It's 3 planes where they intersect. Now we have to solve this. And that's something you did in 1414, Math 1414, college algebra. And it's, never did it? No? Okay, it's okay if you didn't. You should be able to do that by hand. However, in like a calculus class, at least in my calculus class, I don't go back on how to do that by hand. We use our calculators to solve these systems of equations. So what I'd like to do right now is let's just show of hands. How many of you have a TI calculator, TI Texas Instrument, that's a graphing calculator? Yours might. I don't know. Anyone not have a TI? Well, not. Do you own one or do you have one? You don't have one? Do you have a graphing one? Okay, please bring that next time. Do you have access to one or no? No. I have a few spares. I don't mind loaning out, like, I think I can come up with maybe 3. How many do I need though? 1, 2. You have one though? Okay. You have one? Okay. You have one. Okay. So what I'll do is I will bring the graphing calculators next time. And what we will do is I will show you how to use your graphing calculator to solve the system of equations. All right? But if you solve it, you will get the answers we just got. Okay? This is the long method, but it always works. In Calculus 2, there are problems that we do where we get a system of 6 equations and 6 unknowns. 6 equations, 6 variables. You don't want to do that by hand. So we use, technology to help us. All right. Ready for something new? Not new, like we're still doing partial fractions, but you ready for another twist? Of course you are. Partial fraction, this is what we should have started class with. Like all the other pre-calc classes started the semester with partial fraction decomposition. And I think the reason they do is just kind of like wake people up. Like, you got a lot to do here. All right, so let's try something else. And I don't know why they avoid that on purpose in this book. I don't know. All right, we'll do this one. It's in the book. 3x minus 5 over x cubed minus 1. Break that into its partial fraction decomposition. First thing, degrees, right? Is the degree of the numerator smaller than the denominator? Yes. So we move on, and we try to factor out the denominator. Does the denominator factor? Yes. You should recall a formula for difference of cubes. And if you don't, there it is. That's your difference of cubes formula. There's also a sum of cubes formula. And these are on your formula sheets, somewhere on there. All right, so this is, just replace your y with 1 and rewrite this, because that's what we have up there. And this becomes 3x minus 5 over x minus 1 times x squared plus x plus 1. Yes. So that's just me replacing all of these y's with 1's. A little piece of useful information. If you ever use a difference of cubes formula, this is going to be a quadratic, right? You're always going to get this little quadratic thing here. That will never factor. Never does. If it did, then the formula would factor it for you. Like they would actually have factored it out more in the formula. But the formula implies that this cannot be factored further, which means that this cannot be factored. So you remember there are some quadratics that we can't factor? We call them prime. What we have here, and this is the first time we've run into this, is we have a distinct linear factor, right? This is a linear factor. And then we have a quadratic factor that cannot be broken down. And these have technical names. So this is a linear factor. And this book calls this an irreducible quadratic factor. We have not seen this. This is brand new, okay? How do you think we're going to deal with this? When we write this out, we know it's going to be split up into a couple of things, but what about that linear factor? What do you think we're going to get over here? Just x minus 1? And then on top, maybe a? Yeah? That's right. That's exactly what we get. What if this had been x minus 1 cubed? X minus 1 cubed. And then b over x minus 1 squared, then plus c over x minus 1 cubed. And that would suck, but that's what we would have, right? Okay. How about irreducible quadratics? This is the first time we've had a quadratic that can't be broken down. So what do we do with it? Well, what we do is we slap the irreducible quadratic here, right? But on top is not going to be a constant. Any idea on what it might be?
B minus x minus c.
Okay, so if this, I told you that this up here, this was linear, right? And what goes up here was 1 power less. So if this is quadratic, what should go up here is linear. So what should go up here is bx plus c. See how bx plus c is a linear expression? That's linear. If you give me a number b and a number c, then that would be a linear expression up top. Quadratic on the bottom, linear on top. Linear on the bottom, constant on top. What do you think would happen if you had an irreducible cubic on the bottom? What do you think would be up top? Quadratic. But we're not going out that far. We only, even in Cal 2, we only go to irreducible quadratics. We don't go past that. All right? Sure? Any idea or guess as to what would happen had this been irreducible quadratic cubed? You would have bx plus c over this, then another maybe like dx plus e